share. Okay. Oops. Chat. Okay, so we stop at. Have we covered E-beam? We haven't covered E-beam, right? E-beam evaporation? If I'm not mistaken, not yet. Okay, have we covered or sputtering already? Not yet, right? Okay. So let's have a look into E-beam and sputtering today. E-beam. Okay, so we have discussed about thermal evaporation and we have watched that short video on thermal evaporation. So another evaporation process is called E-beam evaporation, electron beam evaporation. So if you can recall, thermal evaporation is limited to typically low melting point materials or generally metals. So sebelum ni saya mention about 1000 degrees C and the corresponding vapor pressure for each material. So typically we can evaporate up to 1000 degrees C melting point of any material. So beyond 1000 degrees C, we normally go for other deposition methods such as E-beam evaporation or maybe even, right? As far as PVD is concerned. So if you recall PVD, physical vapor deposition, so you have evaporation and sputtering. For evaporation, we have E-beam and thermal. For sputtering, you have DC and RF, right? DC and RF. So we're going to go through sputtering later on. So electron beam evaporation is a little bit more complex as compared to thermal evaporation, but it's more versatile because it can accommodate more materials to be evaporated. You can even use materials that you can use on thermal on E-beam. So maksudnya you can even evaporate low melting point materials on E-beam, but you cannot evaporate high melting point materials on thermal. Okay, you can use wider range of materials, but then it's more complicated as far as the operation is concerned. You can see on the video that thermal evaporation is very simple. You just evacuate the chamber down to about -5, maybe -6, depending on the type of materials you want to evaporate, and then turn on the current, turn on the knob, and then make sure that your solid material melt, and then wet your tungsten board, and then they're going to evaporate in gas phase, and then they're going to land and solidify on your substrate. So whatever your substrate is, silicon or glass or some other stuff. Simple. On the other hand, E-beam, it is more complex, but serve wider range of materials to be evaporated. So can achieve temperatures in excess of 3000 degrees C. So that means you can evaporate high melting point materials such as titanium, palladium, platinum. You can even evaporate ITO, silicon nitride, right? Silicon nitride, if you try to go for thermal evaporation, then you will not be able to do that unless you have a specific system that can deliver a very high level of current to the material. So to share with you, last time I tried to evaporate a silicon nitride powder on thermal evaporation system that we have in our lab. So because the current is not high enough, it can, so nothing happens on the boat. Nothing happens on the boat. So you will still have silicon nitride left as the original condition. So nothing has changed in the process after I vented the chamber back to atmospheric pressure. And I also tried silicon nitride powder to be evaporated on another system of thermal evaporation where higher level of current can be used, but silicon nitride still cannot be evaporated because even though you have higher current delivered to the boat for the melting process. Kalau dia punya melting point is too high, what's going to happen is the high current through material to be, dia akan melompat dan keluar daripada you punya boat. So nothing actually happens. So current tu terlalu high, but then it is not enough to melt your material, so they will just jump off the boat. And bila you vent the chamber, masuk pressure, you buka chamber, you tengok dia punya powder tu dah tak ada kat situ, semua kat bawah on the floor, right? So nothing happens. So that's why you need another system to do the job. So in this case, electron beam evaporation, or in fact, can also consider sputtering process. So use evaporation cones or crucible in a copper condition. You need to use high emission voltage in order to bombard your precursor material, right? So it involves a magnetic field as well to steer the direction of your bombardment, so that you punya beam tu akan hit the material. So you're gonna see later on the next illustration. In fact, you can watch the video attached on the slide as well. Saya ada add juga satu video on e-beam evaporation on e-learn. You can watch that as well. The schematic of the process and then the animation of what's actually happening before the e-beam evaporation takes place. Typical depth rate is higher than thermal, so it's 10 to 100 angstrom per second, so that's like 1 to 10 nano per second. Common evaporant materials or common precursor materials are as listed: nickel, platinum, iridium, ruthenium, titanium, vanadium, zirconium, tungsten, tantalum, molybdenum, and all the dielectric, or in fact oxides. ALOX, silicon dioxide, silicon oxide, dioxide, tin oxide, titanium dioxide, zirconium oxide, and the list goes on, right? So you can do a wider range of materials. So this is how it looks like. Well, a system can, for your information, an evaporation system can be either thermal or e-beam depending on the configuration inside the system. And it may look the same, but you need to look into the heating mechanism. Either it's by resistive heating, which is for thermal evaporation, or by electron beam, right? So this is how it looks like. So you can see on the left hand side illustration here, you have e-beam source coming out at a very high voltage, or that will be the emission voltage. You can see this one clearer on YouTube. Then it will be bended by magnetic field in the system, right? So it will then be bombarded onto your evaporant materials or the precursor materials that will then evaporate, just like the way you have evaporation in a thermal system. Yang lain semua sama, the chamber and in fact the vacuum. I can't draw this. I thought it cannot. Chamber will be something like this as well, sama aja macam your evaporation system. Usually the e-beam pressure is slightly lower because of the the condition that it needs to go through in order to do the evaporation process. So typically 10-7 and -8 is a typical range of the base pressure for this system. Whereas if you go for if thermal evaporation, 10-5 is typical as the base pressure. Okay. So this is the zoom in version of the previous illustration. You zoom in, you get this. Cathode filament, high voltage, and then you have magnetic setup, magnetic field in the system to bend the beam 270 degrees C to heat your evaporant materials at a very high voltage, and then you're going to have your evaporation to your substrate. So you need to use cooling water as well, because the process uses high voltage, high temperature system. So you need to use cooling water to constantly cool the system, or else you may end up burning the system. Right, so this is the mechanism. Yang macam tadi saya explain, you can actually see this on the YouTube. Sekejap hang tadi I don't know why suddenly hang. Let me reshare. Now can you hear me and see me? Tiba-tiba hang tadi. Saya minta sedar. Okay, let me reshare. The whole thing shut down. I need to. Jom saya buka balik file. Okay, hold on. Sorry. Let me. Okay, can you see the slides now? Okay. All right. Let's continue. Okay, so you can see the mechanism on the YouTube video on the link, right? On the animation, macam mana the punya beam tu is being bent to hit the precursor material to enable e-beam evaporation. So you can also use multiple pockets. Multiple pockets process means if you want to evaporate compounds, for example, we discussed about the CZTS, then you may need to use multiple pocket deposition because the vapor pressures and the melting points for different materials are different. So if you use different pockets, so that means you need to control every single pocket independently. For example, if you talk about current level and rate of increase, they have to be different respectively. So maksudnya bukan single control for all. So you need to use 4 different knobs for the current, for example, in order to get your evaporation done. Okay, let me click this. Let me share. Okay, you can see the YouTube page, right? Okay, so need illustration of the system, so that you can see the shutter as well. So that could be different pockets. Well, this one is only a single pocket, but then you can assign different pocket for different materials. Then you can just swap during the operation. So on the side here is the crystal monitor to monitor the deposition rate and the thickness. So that's the bending of the beam. That's the evaporation. So now being blocked by the shutter. Then the shutter will be open. So yeah. So that's the bending, the evaporation, the detection by the crystal monitor on the right hand side to know the deposition rate and the actual thickness. So your sample is up there on the holder. So this is the guy, the thickness monitor that will monitor the deposition rate. Either it's too high or too low, or nothing is being deposited. So now it's done. So you vent the chamber back to atmospheric pressure, and that's it. Right? Just a simple illustration about the e-beam evaporation process. Okay, now let's go back to the slides. Okay. All right, so thermal versus e-beam. Thermal is on the left and e-beam is on the right. So thermal is based on resistive heating or Joule heating. You can see different configurations of both systems. The one on the left, thermal evaporation, they use current to melt the sample, and then you're going to have your evaporation right to the substrate. And for e-beam, you use electron beam, as the name implies. Beam has to be generated, and then it has to be bent by 270 degree to heat the precursor material before you can have your evaporation process. So both systems or both processes are considered line of sight deposition, right? So evaporation is a line of sight deposition. So you're gonna need to make sure that your samples are perpendicular to the precursor holder, so your source. So sama juga dengan electron beam, you have to make sure that your precursor is aligned to your substrate or to your wafers as well. We won't have much problem with line of sight deposition if you do your deposition on planar substrate, right? On your planar substrate. Kalau you nak, for example, katalah this is your substrate. So for example, this is your wafer, silicon wafer. You want to e-beam evaporate ITO, for example. So ITO will be coming from here. So normally we won't have a big problem on the quality of the ITO, on the properties of the ITO deposited on planar substrate. But if you want to deposit on textured substrates, for example, if you have the very same silicon, but instead of planar, they are textured, they are rough. So the surface is rough. So deposition of ITO or some other materials using a line of sight deposition can be a bit challenging because some areas will experience shadowing effect. Kita belajar shadowing effect, line of sight deposition, right? Okay, so in this case, some of the areas on the textures may not have enough ITO. Say if you intend to deposit around 100 nanometer of ITO, so you may end up some areas. So maybe some areas will have 100 nano as intended, but some areas, some other areas, particularly on the steep angle, only have like 30 nanometers. 30 nanometers. So it's way lesser than the intended thickness, right? So then the properties of your material, of your ITO, maybe the transmission, the reflection, the absorption, the shear resistance, conductivity of the ITO will not be as expected because of the lower thickness problem by shadowing effect. So I faced this problem when I did my PhD last time because I used electron beam evaporation to evaporate 10 micron of silicon. So it's actually amorphous silicon, but later crystallized. But I did my deposition on glass. So saya buat solar cell, but my substrate was glass, and not only glass, my glass was textured. So I have like a steep angle on some areas of the glass, for example, and then some areas, if you do deposition of thick material, for example, if you deposit 10 micron, this shadowing effect may not be a big problem because your material is thick enough to be noticed on the steep angles. Right, so tidak tebal, maybe you'll probably see 10 micron everywhere, and then some areas you're gonna have like 9.8, 9.7 micron instead of 10 micron, and that doesn't give you significant effects in terms of properties of the material deposited. But in my work last time, I did deposit dielectric layer as well using e-beam evaporation on textured glass, and the layer thickness is like 50 nano, and some is like 100 nano. So the layers are very thin, and these steep angles on the textured substrate will show as a significant problem in your device or in the material later on, right? So when I deposited 100 nanos, some areas ended up like 30 nano or 20 nano, particularly if you have a very steep angle. So the steeper the angle, the more problematic the shadowing effect will be, and the more effects you will see on the device. But as far as planar substrates are concerned, usually it will not be that critical because you get to rotate your samples during deposition, so the samples will experience rather uniform coating or deposition during the process, so it's not a big deal. But for textured substrate, even though you do rotation, you will still experience some problem due to shadowing effect on textured substrates. Okay, so now let's continue with sputtering. Sputtering is another PVD process, so physical vapor deposition process. So in thermal evaporation and in e-beam evaporation, we discuss about evaporating the materials off the source. Okay, so on the other hand, sputtering is another mechanism. So sputtering is a process in which particles or the atoms or the molecules are physically knocked off. So knocked off means you dislodge. You need to have a sputtering target. Ada any of you pernah buat sputtering before in your FYP? I know Izyan and Fazira. Ada yang lain pernah buat? Jenny, you did sputtering, right? Jenny? ITO and zinc oxide, isn't it? You dengan Cingwe kan? Betul? Ada lagi yang buat sputtering process? So this is the mechanism that you have used last time. So it's dislodgement of atoms or molecule. You pergi kat atom, tenang keluar. So you dislodge the atoms or molecule from its original position. And the original position is in the sputtering target material. So if you're sputtering silicon, then you are knocking off silicon atoms off the target to fly in the vacuum environment to get to the substrate. So the same goes to ITO, zinc oxide, aluminium. You can in fact sputter the materials that you can evaporate by thermal evaporation. You can sputter aluminium, you can sputter silver, you can sputter dielectric, you can sputter conductive oxide. So it's a wider range of materials that you can sputter, right? So the atoms or molecules will be physically knocked off. So dia akan ditendang keluar daripada target, ejected from a source target. So this is the sputter target, using energetic gaseous ions in plasma, right? So the plasma here that we use is argon. So it's argon plus. So you need to inject argon gas into the chamber and then apply electrical supply to the argon to initiate formation of plasma. So plasma is ionized gases, right? Ionized gases. So argon, you strip off outer electron from the argon, then you're gonna get argon plus, and argon plus is the plasma that you're gonna use for the sputtering process, right? So you can see argon plus in the illustration here in the yellow region, just to illustrate presence of plasma, and argon ion, right? So you're gonna have like hundreds of thousands of argon ions in the vacuum. And the process is done in the vacuum environment as well. So you can still recall, Jenny, last time, what was your base pressure during sputtering before you start the plasma? Ingat lagi, what was your base pressure? You need to pump down sebelum you start plasma. Ingat lagi? What's the value like? What's the range of the pressure for the base pressure? Yeah, somewhere -5, right? So you need to use base pressure of about -5. So that's called base. Oh, sorry. That's called base pressure as well, just like what we call in evaporation. So base pressure is typically about -5 torr, right? So the moment you have reached your base pressure, you need to inject the gas. The moment you inject the gas, what do you think will happen to the pressure? Sekarang you -5, then you inject argon gas before you initiate plasma. Apa jadi dekat pressure? Will it be maintained or increase or reduce? Ini basic, basic. So what's going to happen? This one, this side here is 10 minus 5 now. Before argon, sekarang kita inject argon sebab kita nak kena create plasma kan. So what happens to the pressure inside the vacuum? Jenny, still remember? Oh, Chingwei, you still remember? What happens to the pressure the moment you... Alamak, where's the page? Here. What happens to the pressure the moment you injected the gas? Chingwei, remember? The pressure? Oh, Jenny, remember what happens to the pressure the moment you injected the gas? Apa jadi kat pressure? Increase. Sudah lupa ke Jenny? Kalau you, last time we discussed about evacuating the chamber, right? Kalau you remove particles, pressure will, you remove particle, guna pump, pressure will, guna pump, you reduce, you remove particles, apa jadi kat pressure dalam space tu? When we discuss about vacuum technology. Yeah, pressure decrease, right? You remove particles from the space. So you now have less particles or atoms or whatever, molecules, moisture. Then pressure decrease. You get your vacuum from atmospheric as your original condition. Sekarang you reverse the process. You pump in argon gas into the vacuum at -5. So apa jadi dekat pressure dalam space tu? Increase or decrease? Saya dah bagi clue tadi kan? Reverse the process. Apa jadi? Reverse the process. What happens to the vacuum? Increase, right? Increase. So tadi kita mula-mula kita bila you start you punya lab, you start from atmospheric pressure, and you use vacuum to evacuate the chamber to -5. Sekarang you already have a vacuum, but then you cannot have a plasma, right? Because it's vacuum. Tak ada apa dalam tu. You cannot initiate sputtering process because, well, you already have the vacuum, you have a target, you have your substrate. So what's next? You need to use plasma in order to initiate the process. To do the sputtering, you need plasma, high energetic ions, in order to dislodge the atoms or molecule. Kalau you pakai something that energetic, then you won't have any dislodgement, or nothing will be knocked off because the energy is not enough to do the job. So you need plasma. In order to do plasma, you need a gas to be ionized because plasma is an ionized gas. So you need gas. Then you inject the gas. You inject the gas, you add on particles in the space. Then maksudnya you actually reversing the process, right? So pressure akan increase. Pressure akan increase up to, usually, it's going to go to about 10 minus 3 torr. Ataupun we call it whatever millitorr lah. 10 minus 3 torr. So you notice that the pressure has now increased by 2 orders of magnitude by injecting the argon gas before you have the plasma, right? So that's the sequence. Evacuate, -5, base pressure, stable, inject gas, it goes up to -3 or millitorr. Then you supply the electricity required, the voltage, whatever required, in order to initiate the plasma. Strip off the valence electrons of the argon gas, get argon plus, get more of argon plus. Now you have plasma formation, right? Plasma formation. How do you know you already have a plasma inside the chamber? Fazira ke Izian ke, you did sputtering, right? How do you tell you already have the plasma in the chamber? Any ideas? From your silicon nitride deposition last time? Any idea? Jenny, how do you tell you have a plasma already in the chamber? Yeah, you can see the light, right? So you can see some color. So Chima, you still remember what's the color of your plasma last time for your sputtering process? Red, is it? Light purple, right? Purple, well, this one depends on the gas that we use. Nanti try check. Kalau argon barat, kena tengok color apa. Kuning dalam saya punya slide ni is just example lah, bukan plasma color kuning. So it will give you some color, right? Kenapa plasma ada color? Why do you have color from plasma? Anyone? Plasma. Why do you have color from plasma? Why is plasma why plasma comes in color? Nanti you check lah. Banyak mana you kena check ni. Mana tahu jadi soalan. Photons, alright, photon. Where do you get the photons? Where do the photons coming from? In the plasma chamber. Yes, if you see color means you are seeing plasma, right? Sorry, you are seeing photons, right? You're seeing something visible, photons. Nanti you try tengok macam mana you dapat photon dalam tu. Aren't we removing the outer electrons from the argon and turning the argon into ions? Then kat mana photon tu? Right, di manakah photon itu? Dari mana ia datang? You try check nanti. Right, this is also another PVD technique, physical vapor deposition. So that's the simplified mechanism, right, of plasma formation and to enable sputtering. So the moment you already have your high energy ions, argon ions, so argon ions will bombard your sputtering target. So argon ion akan tendang all the materials out, dislodge or knock off all the ions, or the molecules at some rate, right? This rate is called sputtering rate. How strong is your dislodgement process? It's called sputtering rate. Ataupun you can, in fact, you can measure using a crystal monitor that we saw just now on the video for YouTube, for e-beam. Tapi dia punya konsep dia sama aja. Thermal ke, e-beam ke, sputtering ke, dia punya common setup dia lebih kurang je. Cumanya the way you produce your plasma ke ataupun the way you initiate the process will be different, and that will give you the name of the process: thermal, e-beam, sputtering. So that's the mechanism where you get the deposition done. But other stuff like chamber, holder, argon, mungkin yang PVD tak ada argon lah. Evaporation dengan apa tu? E-beam, right? The rest are usually similar. Substrate temperature, vacuum level, more or less similar, right? Then you will have your sputtering from your sputter target to your deposited substrate. Either silicon ke, gas ke, glass ke, ataupun some other substrate. So it involves momentum transfer from the incident atom to the surface atom in the target material. So incident atom or ions are from energetic plasma, energetic argon, Ar plus to the surface atoms in the target material. Do you notice, for those of you who did sputtering, do you notice the look of your sputter target? You nampak tak ada macam bekas dekat sputter target? Fazira ke, Izian, do you notice anything on the sputter target? Usually when you buy a new target, it will be a flat sputter material, sputter target. But over time, you will have some macam berbekas sikit. Do you notice anything on the target? Kuat pula orang potong rumput dekat bawah. So you notice some what you call some shape on the target material. Nanti kita akan tengok kenapa. At energy lower than bonding energy, you normally have high energy in order to enable the dislodgement ataupun knocking off. Impinging particles to be embedded in the target ion implantation. Well, you can have some conditions ending up as implantation, right? But this one is very rare. Lattice damage and sputtering process. So in some condition, you may the particles ataupun atoms ataupun molecules from the sputter target landed on the substrate can also induce some damage to the substrate to some extent, right? You can also use sputtering system. If I can go back. Okay, for example, if you look at the configuration here, you can in fact, you will what you call, customize the system lah. Usually when I talk about evaporation, sputtering, CVD, you can actually customize the system. So after you have customized, then maybe a new name will be published. You can call it as a new name, like hot wire or whatever. So for example, for this particular system, you can connect the substrate holder. So this one is your substrate. Dekat atas is target. Just sputter target kat atas. So for example, you want to sputter zinc oxide. So this will be zinc oxide. And this guy on the other side is maybe silicon. For example, you want to sputter zinc oxide on silicon. This silicon can be connected to negative polarity. You can actually apply bias to the substrate, and you can also apply bias to the target. So when I was in Fuji Electric last time, when we were developing hard disk drive, 1 terabyte on aluminium and glass substrate. So we did apply some negative bias to the substrate. So in this case, on this side. So when you apply negative bias on the substrate, what do you think will happen? What will happen to the surface of the substrate? Apa yang you rasa akan jadi kalau you apply negative bias dekat substrate? Kalau you apply negative bias, the substrate will be negatively, will be on negative polarity more or less, right? So what will happen is you have argon plus in the plasma. So argon is positive and your bias is negative. So negative will attract positive. So you will attract more high energy ions to the surface of your silicon. So you can also etch your silicon at the same time while doing the sputtering. So yeah, you will have your zinc oxide deposited on the silicon. At the same time, you will also have some etching to the silicon. So this is like etching in sputtering. You can do that, okay? So that's why saya cakap you can customize. Kita guna kita punya basic physics where negative attract positive. So in this case, negative polarity attracts all the argon ions to be colliding on the silicon surface and do the etching process. As if you are using plasma to do etching, plasma etching. So you can etch the surface, you can customize the roughness of your silicon by having bias on the silicon. Roughness because of more bombardment of your plasma on the silicon surface. So while having deposition, you are actually doing etching to the substrate. So this is what we did last time when we tried to develop 1 terabyte, or in fact more than that, on glass and aluminium on sputtering chamber dalam Fuji Electric. Yeah? So it was like 20 chambers in series. One chamber is for one layer. So each layer is ferromagnetic in nature. So you're going to have like ruthenium, titanium, all the titanium plate dalam periodic table to be able to do the magnetic storage, right? So the goal is to store more data on the plates of the same size. So we then have to develop our own process by using sputtering. So you have like 20 chambers, 20 layers to play with. Bottom line, you have to have more storage on the same area of your substrate, aluminium or glass. So let's see the sputtering video here before we end the class. Oh, sorry. Copy here. On the YouTube already. Oh no, this is. Oh, sorry, this is evaporation. I copied the wrong thing. Hold on 1 minute. Okay, let me share this and then we go through 2 minutes video and then done. Okay, can you see the YouTube page? Nampak? Okay, so let me just play this 2 minute video. So what is sputtering? So that's the chamber. So these two stuff are your target materials, right? So you have target 1 and 2. So you have mechanical shutter on 1 and 2. So that will be your chamber. Target 1, target 2, shutter 1, shutter 2. So this whole space will be in vacuum. So this is the species, the radicals. We're going to come to this later on in the next few slides, maybe next week already. So this is now at vacuum level. So now you have, you apply electrical potential. So you dislodge the atoms or molecules from the sputter target. Shutter is open, so now you can have your deposition running during the process. The electron from the electrical supply strip off the outer electrons from the gas, initiating plasma. So these are the target materials. You can see the atoms and molecules there. So they are dislodged one by one, in fact more than one. So just to illustrate the process, you can see now, so materials are being deposited onto your substrate. So the substrate is rotated to ensure uniformity. So they're going to be a recombination process. So we learned recombination last time. So the recombination gives the emission, light emission, the plasma, and sustain the plasma, because you're going to have like recombination constantly going on during the process. So you're going to have like plasma is sustained during the process. So that's how you get plasma. You get to see the plasma. So that's the plasma. You can see the color. You can see the rotation. Shutter is open. Deposition takes place. So this is the plasma system. So the size ranges from a small one to a very big one. Some run with a simple one chamber, some multiple chamber, some range of chambers in series, depending on the device that we want to fabricate. Let me just show you argon plasma. Argon plasma. Maybe for sputtering. Okay, so this is how it looks like, more or less. You boleh check kalau different gas dia akan bagi different plasma color. So this is argon plasma. It's like purple sikit . So you can see through the glass window. So if you don't see any color, means there's no plasma being initiated. Ataupun tiba-tiba you tengah run deposition process tak habis lagi, tak cukup lagi, then you see there's no plasma. So that means your plasma dies off due to some reason in the system. So that's how it should look like, right? So it should be sustained throughout the whole process sampai you stop the deposition. Even though you stop the deposition, you tak matikan plasma lagi, you just close the shutter on this one is your target material, ada opening. So shutter is open during your deposition. After the process, plasma is still there, but you just close the shutter. That means the plasma yang hit the material pun dah minimize lah, then you close, then only you stop the process. So this is another one, more or less. You can explore later on YouTube. So more or less that's how it looks like. The system, the mounting, the copper plate. Now this magnetron. Magnetron kita akan discuss next week lah. Why do you need to use the magnetron? Okay. Okay, so I'll just stop there. I'll see you again next week. All right, any questions on evaporation or sputtering? Esok cuti, tak ada kelas. So I'll see you Monday then. Okay, no question. All right, so yeah, see you next week. Bye-bye, take care. Assalamualaikum. Have a great weekend. Tomorrow is weekend already. Bye-bye.